Okay, in this screencast we're going to have a look at the concept of exponential growth, and specifically one of the areas we're going to look at is compound interest at the financial example of exponential growth. So if I've just set up a little population axis here, so population on the vertical, time along the horizontal, just to demonstrate the concept of exponential growth. Exponential growth just refers to the growth of a population or a bank account or whatever the case may be, but as time goes on at greater rates. So the growth we call it exponential when it gets increasingly larger and larger with time. So let me just do an example. Let's just say that in this population, it's a very simple population model we're going to illustrate here. At time 0, so initial population is 100, so I'll just pop 100 down there. Now let's just model a 10% population increase. So 10% every year. So after 1 year, this population of 100 has increased to 110. So we'll plot that point there. So now we've gone from there to there. But that same 10% now, we're going to experience the same 10% growth, but it's now on a population of 110, and 10% of 110 is 11. So when we add that on, our population after 2 years is now not 120, as in that would be a steady state increase. It's now 121. So it's just crept up slightly. And now for the 3rd year, when we apply our 10% increase, it's on 121, which is 12.1. And when we add that to 121, we get 133.1. And so we just creep up again, just off the linear again, just edging our way up. And if we keep applying this, we're going to just slowly but surely start edging our way up. And so if we graph this model here, it's just increasing, and as the population increases, this just gets steeper and steeper. It's called exponential growth, and it's typical for studies of populations, and also for compound interest. If we have a look at a model let's have a look at a compound interest model. So let's say that we invest $10,000. $10,000 is invested at let's say 8% per annum. Compound interest. Now, all compound interest means is that interest will be earned on current balance. So interest revenues are added on to balances, and then the interest is calculated on that. So it's an ever-increasing exponential style growth in this style of investment. So 10,000 invest, and I should say it is what banks offer when they offer these sorts of investment opportunities. Then that's this compound interest model is what they are using to calculate the returns on these investments. So 10,000 invested at 8% compound interest. So let's have a look at what happens after 1 year, what it's worth. So after 1 year, what do we have? Well, what I want to draw on here is our knowledge of percentages. So after 10,000, so what we're doing here is we're finding 8% of 10,000 and we're adding it on, and that's our new balance. But to do that in one step, if you remember your work on percentages, to increase 10,000 by 8%, we multiply by 1.08. Just as if we wanted to reduce 10,000 by 8%, we'd multiply by 0.92. 1 being no change, and above 1 being an increase, and below 1 being a decrease. So after 1 year, that will be our return, which if we put into our calculator, 10,000 times 1.08 is 10,800. So that is now our balance after 1 year. That balance then gets taken into the 2nd year, and the investment now earns 8% in the 2nd year, but on the new balance. So the new balance is 10,800, and we times that by 1.08 to get our balance at the end of the 2nd year. So back into our calculator, and what we do here is multiply by 1.08 to increase that amount by 8%, and we get 11,664. we get 11,664. So what we've got here is, and we can continue this down, but what if we wanted to, say, calculate what the investment was worth after 10 years? So what we want is some formula to work with. Now you might have noticed here that we started with 10,000 and we multiplied by 1.08, but then what we did with that amount was we multiplied by 1.08 again for 2 years, and then with that amount we'd multiply by 1.08 again. So all that's happening is that this power is increasing by 1 each time, and for 10 years it'll be a power of 10. So a quick route to find out our solution here would be to take 10,000 and multiply it by 1.08 to the power of, well, made a mess of that. This happens a lot with this thing. 10,000 times 1.08 to the power of 10. Here we'd enter, we got 21,589.20. 21,589.20. So our investment has in fact it's doubled, or more than doubled, in 10 years. So you can imagine with a larger quantity of money, the sort of growth you get on your finances based on this model of exponential growth. Because you can see the first year it's a fairly modest increase of 1,000, but then it's not, we're getting more and more each time, because now we're taking 8%, 11,664, and it goes on and on. So that's how we're going to calculate compound interest. And if we want to just write down a formula for compound interest, compound interest formula, one to work with is A being the amount that the investment comes to, A naught being the starting amount. We take 1, interest rate over 100 to the power of t, and each of these has, so A is the final amount, that's the initial amount, A naught being the initial amount, R being the interest rate, as a percentage, and T being the compounding period, the time. Okay, so that's a fairly straightforward formula in order to calculate compound interest investments. Okay, we can look at an example where we have a decreasing population. So we're just taking this example out of the textbook, or I might just make up another one actually. A car depreciates, so everyone knows that cars depreciate in value. Car depreciates at, let's say, so let's make it quite high, 12% per annum. It is bought in 2015 for $41,000. Bought in 2015, we'll say January 2015, in January 2015 for $41,000. What is it worth at the end of 2020? So at the end of 2020, we have, I want to say in January 2020, just so that we've got an even. So what is it worth at January 2020? So that's 5 years down the track. So what we've got is a starting, we apply the same formula, except we're not going to hit plus here, we're going to hit minus. So our amount will equal our initial amount, which is 41,000. We're going to take 1 minus our interest rate, 12 over 100, and we're going to raise it to the power of 5. So this in neater form will look like this, times 0.88 to the power of 5, and into the calculator, 41,000 times 0.88. So this is a depreciation of 12% depreciation per annum over 5 years. It's now worth 21,637. I don't know how 21,637, it's almost halved in value in 5 years. I don't know how realistic that is. Depreciation values are probably quite constant when it comes to new cars anyway, so that's a scary feature of someone who's just bought a new car. Okay, that's probably going to do us for now. We're ready to go then when we get into class on Tuesday to do exercise 3K from starting at page 209. Okay, I'll see you then.